Welcome everyone. Today what we're going to do is we're going to use something called formal charges to determine what is the most stable Lewis dot structure for a given compound. And as you can see at the bottom here, we have a formula on how to find formal charge. What we do is we get the valence number or the valence electrons for that particular atom, and then you subtract it minus half of what is called the bonding electrons. The bonding electrons are the ones that form bonds. Remember that we represent a bond with a stick. So a single bond, which is one stick, counts as 2 electrons. So double bonds, you'll know, count as 4 electrons. It's 2 sticks. Triple bond would be 6 electrons. Because in that stick, each atom is sharing a pair of electrons. And then you subtract it by what is called the non-bonding electrons, which is simply the dots, which are the lone pairs. We're going to count those individually. Now, what I'm going to do is I'm going to show you a modified way to figure out formal charge. Basically, what we're going to do is we're going to get the valence electrons minus, instead of saying half the bonding electrons, if you just count the sticks, that already would be the number of half the bonding electrons. Remember, a stick is 2 electrons, so half of 2 is 1. So counting just the stick itself would already do this for you. Now the dots, which are the non-bonding electrons, the lone pairs, those we have to count individually. Let me show you what I mean. Here's an example. This is the cyanide ion, and we're going to find the formal charge of both carbon and nitrogen. So here's what we do. Let's look at carbon first. To find the formal charge, you first find the valence electrons for carbon, which from the periodic table, it has 4. Then, minus what is called half of the bonding electrons. The way that I do it, that is much easier, is basically count the number of sticks. The sticks are the bonding electrons. There are 3 sticks between carbon and nitrogen. There's 3 sticks surrounding carbon. So there are 3, what we call bonding. Then minus the non-bonding, which is actually the individual dots around the carbon. There are 2 of them right here. So 4 minus 3 is 1. 1 minus 2, you get a negative 1. So carbon here, if you look here, 4 minus 3 minus 2, you have a negative 1 charge here. Now let's take a look at nitrogen. The valence number for nitrogen is 5. How many sticks do you see around nitrogen? There's 3. And there are 2, which would be the non-bonding. So 5 minus 3 is 2. 2 minus 2 would be 0. So the valence number for the nitrogen is 0. So we've assigned formal charges for each. That's how you calculate the individual formal charge. Notice that this is an ion, and notice that the sum of the formal charges will be equal to the charge of the overall ion. There's a net negative 1 charge. Now let's take a look at a more specific example. Here we have 2 ways to represent carbon dioxide. Now we know from experience here that the one on the left is the structure for carbon dioxide that is always seen, but we're going to propose a second structure on the right, and watch how we use formal charges to determine which one's more stable. So let me show you how they got these numbers. First, the oxygen on the left, the valence is 6 for oxygen. There are 2 sticks surrounding oxygen, so minus 2. And oxygen has 4 non-bonding or 4 dots. So 6 minus 2 minus 4 is 0. And the oxygen on the other side is identical. The 2 oxygens are identical. So now you know how they got these zeros. The carbon in the middle, carbon has a valence of 4. There are 4 sticks around the carbon. So 4 minus 4, there are 0 dots around the carbon. And when you add that up, it's 0. Notice there's no charge here. So the sum of the formal charges is 0 because this is a neutral compound. Now, let's take a look at the one on the other side here. The oxygen on the left that has a single bond has a formal charge as follows. The valence is 6 minus the 1 stick around it minus the 6 dots. So when you add this up, 6 minus 1 is 5. 5 minus 1 is -1. So that's how that oxygen got a -1. The carbon is 4 valence minus 4 sticks. The triple and the single makes it 4. There are no dots. So the carbon in the center is 0. And then the oxygen on the other side, the one that has the double bond, or the triple bond, I'm sorry, you got 6 as your valence minus 3 sticks minus 2 dots. So 6 minus 3 is 3. 3 minus 2 is +1. And notice when you add the formal charges, that -1 and +1 neutralize each other, and that's also 0 as a net charge, just like this one. These two compounds are neutral. So let me show you how we compare. This is the rule on how to identify which would be the most dominant Lewis dot structure using formal charges. Rule number 1 says that the dominant Lewis structure is generally the one in which the atoms bear formal charges closest to 0. So you're going to compare, and when you compare, whichever structure has more zeros as their formal charges, that will be the most dominant structure. It will also be the most stable structure. Clearly, the CO2 on the left with the 2 double bonds, all the formal charges were 0 compared to the structure on the right where only the carbon in the middle had a 0 formal charge. That is why this is the most stable and preferred structure for CO2. Now, there is a second rule that we'll look at. It didn't apply here. And be patient. I will show you an example where we have to go to rule number 2 to make a determination. All right, so look at this. Here's our next example. There are 3 possible Lewis structures for the thiocyanate ion. They've been drawn for you. We want to first, in part A, determine the formal charges in each structure. So let's go ahead and do that before we even look at part B. So let's start with the one on the left. The nitrogen there has a valence of 5 minus the 1 stick between the nitrogen and the carbon minus it has 6 dots. So when you do the math, 5 minus 1 is 4. 4 minus 6 is -2. So this guy has a -2 formal charge. The carbon has a valence of 4. There are 4 sticks around it, no dots. So the carbon, 4 minus 4, has a valence of 0. The sulfur has a valence of 6 minus the 3 sticks minus the 2 dots. So 6 minus 3 is 3. 3 minus 2 is -1. So the formal charge is -1. Notice when you tally this up, the net charge is going to be -1, which is what you see over here. These are all -1 charge. Now, let's take a look at the one in the middle. Again, let's do the nitrogen. So the nitrogen is going to be 5 valence minus 4 sticks minus the nitrogen has, I'm sorry, I put the wrong number of sticks there. The nitrogen only has 2 sticks. Okay? And it does have 4 dots. So 5 minus 2 is 3. 3 minus 4 is -1. So this guy's -1. The carbon has 4 valence. It has 4 sticks, no dots. So the carbon is 0. And then the sulfur has 6 valence minus 2 sticks minus 4 dots. And that's going to be 6 minus 2 is 4. 4 minus 4 is 0. Okay? So notice this structure is already better than the first one. We'll take a look at them in a minute. And then we have the one all the way here on the right. Let me see if I can fit this in here. We have the first nitrogen here. It's going to be, the valence is 5 minus 3 sticks minus 2 dots. And 5 minus 3 is 2. 2 minus 2 is 0. So this one's 0. The carbon is valence of 4 minus 4 sticks minus 0 dots. So this has a 0 as well. And then the sulfur is going to be 6 valence minus 1 stick minus 6 dots. That's going to be a -1 charge. 6 minus 1 is 5. 5 minus 6 is -1. So I've assigned the formal charges. Here they are in the next page. They're all written on top. This is what we just calculated. Clearly, this is the worst structure of the three. Only 1 0 as a formal charge. Now, these two, there's a tie. We have two structures that both have zeros. So these two structures are better than the one on the left. So here's what we're going to do. If you recall, I gave you a rule. First, you look for who has the most zeros. Okay? And we know that these are the two better structures. But when there's a tie, this is where rule number 2 comes in. The Lewis structure in which there are the negative is on the more electronegative atom would be generally the more dominant one, whereas having the negative charge on the less electronegative atom. So according to this, notice, and we'll go back to this page over here, notice that the -1 is on nitrogen compared to sulfur. If you recall, and you could see it here when you read the explanation, nitrogen is way more electronegative than sulfur. So you rather have the -1 on the more electronegative atom, which means that the structure in the center would be the most stable. That's the negative should be on the more electronegative element. The structure on the right would be the next most stable. The least stable would be the one all the way on the left. So the first thing you do is you look for the ones with the most zero formal charges. And then if there's a tie, look for that negative being on the more electronegative element in that compound. And that's how you determine this one. So we had to use that second rule here as the tiebreaker. All right, now look at this question. Sulfate can be drawn in multiple ways. Let's minimize formal charge on the sulfur. So our goal is to minimize the formal charge on the sulfur. When you draw sulfur originally, or sulfate, it looks like this. This is the way, and this is a valid structure using Lewis dot structures. If you follow your valence rules and how to draw the Lewis dot structure, you would get this, and this would be a perfectly a molecule. This one would follow the rules. Remember, this is -2. Now, if you do formal charges here, you're going to notice that the sulfur, which has 6 valence, has 4 sticks around it and no dots. So the valence around the sulfur is 6 minus 4 is a +2. And then the oxygens, they're all the same, so it's 6 for its valence. Each oxygen has 1 stick, and each oxygen has 6 dots. So 6 minus 1 is 5, 5 minus 6 is -1. So the sulfur would have a +2 charge, and every oxygen would be at -1. If you tally that up, it does add up to the net charge of -2. You got 4 negatives when you add up the -1s, and the +2 from the sulfur. That does give you a net charge of -2. Now, watch what we're going to do here. We are going to predict by adding double bonds to the sulfur, which, by the way, it can hold more. Remember that sulfur can violate the octet rule because it's from the 3rd period and below. It can hold more. And what we're going to do is we're going to draw this, and let's put 1 double bond here, and let's keep the other ones as a single. And I'll do this accurately, or I'm going to put here the dots. And let's find the formal charges of this one here. Okay, so what we'll do here is, let me go ahead and put the bracket, and let's put a 2 negative here. All right, so the sulfur here in the center now still has 6 valence. Now it has 5 sticks and no dots. So now the sulfur has a +1 charge, which we'll go ahead and write here as a +1. Now, there's 2 types of oxygens. The oxygen with the single bond is still going to be 6 minus 1 minus 6. They're all going to be -1. So he's -1, he's -1, he's -1. But let's look at the oxygen with the double bond. It's still 6, but he has now 2 sticks minus 4 dots. This one ends up being 0. So this structure already is better than the one on the left because there's at least 1 0 here. Okay? So we're looking at a much better structure at the moment. Okay, now let's do this. Let's not stop there. Why don't we add another double bond? So let me go here to the next page here and give myself some room. And if you look here, let's go ahead and put sulfur. And let's make 2 double bonds this time. So when we go like this, and again, let's be accurate here and let's just put 4 dots here, and then each of these have their 6 dots. Let's find the formal charge. Well, we know the sulfur is still going to be 6. Now, there are 6 lines there, 6 bonding and 0. Now, look at this. By having 2 double bonds, we have now minimized the formal charge on sulfur. It's now 0. Okay? Now, let's take a look at the oxygens. We got 1 oxygen. Let's do the ones with a single bond, which is the one on the left and on the right. It's 6 minus 1 stick minus 6 dots. So each oxygen that has a single bond has a -1 formal charge. Now let's go ahead, and if you remember, let's do the one with the double bond. So the oxygen has 2 sticks minus 4 dots. Right now this structure looks really good. We got this oxygen and this oxygen with the double bonds have zeros. If you look here, we're looking for a structure that will minimize the formal charge on the sulfur. Okay, and then for argument's sake, we can even do one more here where we can put another double bond around the oxygen. Let's do this just so we can see how it affects the sulfur in the middle. And this is the one that's going to have 3 dots here, or 3 pairs of dots. So we're going to put a -2 here. And again, the sulfur is going to be 6. Okay, let me not confuse you here. It's going to be 6 is the valence, minus, it has 2, 4, 5, 6, 7 sticks. So the sulfur is -1. So already now we didn't minimize the formal charge on the sulfur. This one went now from 0 to having a -1 charge. We didn't want that. If you recall the oxygens, let's do the one with a single bond so we can stay consistent. So let's do the one all the way on the right. There are 6 valence, 1 stick, 6 dots. That oxygen is going to have a -1 charge over here. And then the ones with the double bond, if you recall, let's do that. You got 6 minus 2 sticks minus 4 dots. Those oxygens will have 0 here, 0 here, 0 here. Okay, so right now when you look, if we were to put another double bond, you'll see that the sulfur will have a -2. Okay, the question is asking how would we minimize the formal charge on the sulfur, meaning what would get it minimized is closest to 0. Well, we actually have a structure. Remember the first 2 structures, it was a +2 here. Then we went to a +1 here. It was this structure where we minimized the sulfur. We got it to be a 0. So they want to know how many double bonds should you draw. Notice that this structure right over here, we had 2 double bonds between the sulfur and the oxygen. So choice C would be the best one. Once we put a 3rd double bond, it goes back to -1. If we put a 4th double bond, it'll be at -2. And the question wants to minimize formal charge. Now, experimental data does provide support that the most accurate structure is the one that we have drawn here on the left. Even though if you put a 4 double bond, the oxygens each have 0, you would be thinking, oh, but that has 4 zeros. The thing is that sulfur, even though it can hold more than 8 electrons, it's violating the octet rule. Technically, it can only hold up to 12 electrons. So it can only really make 6 covalent bonds, which would mean it can hold 12 electrons. We're already violating that with this structure. And by the way, this structure over here would have resonance. That double bond would be alternating back and forth. So this would alternate this double bond can go here, this one can go here, and it just keeps alternating. So that also would show resonance, but the best structure would be the one on the left. Also, if you could argue that if we had a fourth double bond here, the sulfur being -2, the sulfur is not the most electronegative element in this molecule. It's the oxygen. So the structure here puts the negatives where the oxygens are, rather than the sulfur being a -2 charge. So clearly, the structure with the 2 double bonds is the best one. Okay? So I just wanted to give you guys that explanation. Now, here's a nice one for us. Here we got the this is the cyanate ion. And first we want to draw 3 possible Lewis dot structures. So let me go ahead and do that. Let's draw one here. We can put a triple like this. This is one possibility. I'm going to do the brackets because this has 3 resonance structures. So this would be one possibility. You would have to put lone pairs here to give everybody an octet. There is a second possibility here. This is resonance, where we got a double bond between both of them, like this. And we would have to put a couple of lone pairs to give everybody an octet here. Okay? And then there's a third possibility. Let me go ahead and squeeze that in here, where there is a single bond here and there's a triple on this side. Okay, so let me put a lone pair here, and there's a bracket with a negative out here. And this guy has a couple of lone pairs like that. So let's first draw 3 Lewis dot structures. These would be the 3 representations. These all are validated when you follow the Lewis dot structure rules. And then the next question is to see who's the dominant. Well, let's look at the formal charges. See, nitrogen here has 5 valence. It has 3 sticks around it and 2 dots. 5 minus 3 is 2. 2 minus 2 is 0, so his formal charge is 0. The carbon has a valence of 4, minus 4 sticks around it, no dots. He's also a 0. The oxygen here has 6 valence. It has 1 stick around it, and it has 6 dots. So 6 minus 1 is 5. 5 minus 6 is -1. So we're going to put a -1 over here. Okay, let's do the same for the one in the middle. The nitrogen in the middle has 5 valence, minus 2, minus 4 dots. So 5 minus 2 is 3, 3 minus 4 is -1. So his formal charge is -1. Carbon has 4 valence, minus 4 sticks, minus 0 dots. So the carbon has a valence of 0. And then the oxygen has valence of 6, minus 2 sticks, minus 4 dots. So 6 minus 2 is 4, 4 minus 4 is 0. And then the one all the way on the right, the nitrogen has valence of 5, minus 1 stick, minus 6 dots. So let me fix this here. So when we do that, 5 minus 1 is 4, 4 minus 6 is -2, so the nitrogen has a -2 formal charge. Carbon is 4 valence, minus 4 sticks, minus 0 dots. Carbon is 0. And then the oxygen is 6 valence, minus 3 sticks, minus 2 dots. 6 minus 3 is 3, minus 2 is -1. You'll notice that the net charge is -1. When you add that up, this is -1. And -2 plus 0 is -2, and -1 would be -1. They all match the charge of the cyanate ion. They're all -1. Now let's analyze the structures. Okay, let's put a -1 here for the oxygen. The least dominant structure would be the third one, because this one only has one of them has a 0. So this would be the least dominant. So we have a tie here between the first and second structures. We have these two. There's 2 zeros there and 2 zeros here. So we got to go to our tiebreaker, which is always the third option is to compare where that -1 is. So we got a -1 here on the oxygen and a -1 here on the nitrogen. The rule is we want the negative to be on the element who's the most electronegative of the two. Well, if you follow the rules, oxygen is more electronegative than nitrogen. So the most dominant structure here would be the one with the negative on the oxygen, which would be the first structure. This would be the most dominant. The second structure would be the second, and the third structure would be the least likely to find. So that's how we use formal charges to assign to each atom and compare, so we can determine which structure would be the most dominant. Okay, let me go back here. So that's pretty much it. That's how we use formal charges. And, a lot of times they'll actually give you the structures drawn out, and then what you have to do is assign formal charges and then analyze the structures to compare them, and then use those two rules to see who's the most dominant structure. All right, and that will conclude our video.